We are often interested in solving trigonometric equations, that is, equations that involve one or more trigonometric function and where a variable appears inside that function. Many complex mechanisms in physics and engineering can be expressed in terms of a trigonometric equation. And so we want to take a look at how we solve them. So the general strategy that we're going to use for solving trigonometric equations is going to generally be to get a single trigonometric function on one side of the equation and a single number on the other side. Now, this is a very general strategy. The actual steps that you'll need to take to do this are quite varied depending on the problem. You'll need to use facts involving how trigonometric functions relate to one another. You'll also need to use strategies from algebra, such as factoring, the quadratic formula, other algebraic manipulations. But the ultimate strategy is to get an equation that looks something like sine of theta equals a, where a is a real number. Something like this. Then what we do generally is we'll find all solutions in a single period of this equation. Then we add the period multiplied by n, where n stands for any integer. This is the general strategy. It makes more sense when we actually go and do an example. So let's see an example on the next page. Let's try to solve the equation cosecant gamma equals square root of 2. So this is already in a form that we like. We've got a trigonometric function on one side, cosecant, and just a number on the other side, square root of 2. So the next thing that we want to do is to find all solutions to this within a single period of cosecant. So recall that the period of cosecant is 2 pi. So basically what we want to do is find all solutions of this equation that we can find within one complete revolution around the origin. That is, within one range of 2 pi angles, from 0 to 2 pi. Now, to actually find this, we'll want to try to sketch out a couple of triangles on our set of axes that have cosecants of square root of 2. Now, remember that cosecant is 1 over sine, which means that cosecant is positive in quadrants 1 and 2, just like sine. So what we want to do now is we want to sketch out a couple of angles that will be solutions to the equation. We want these red angles to correspond to a couple of gammas that we might choose here. Now, in order for this to work, we need to construct these triangles in such a way that they have a cosecant of square root of 2. Now remember that cosecant is 1 over sine, and therefore cosecant is hypotenuse over opposite. So, to get a cosecant of square root of 2, we want the hypotenuse of these triangles to have length square root of 2, and the opposite side to have length 1. Now, from here, we can either recognize that, oh, this is going to be our 1 square root of 2 triangle, or we could use the Pythagorean theorem to work out that the other side of this triangle has to be 1. We can do the same thing over on the left triangle. We still have the opposite side of 1, and that's given a positive sign because it's going up from the x-axis. Hypotenuse of square root of 2, and then our horizontal side will be labeled -1 because it has length 1, but it's going in the negative direction. It's going to the left. Now that we have these sketched out, we can try to say, all right, well, what's the actual value of these angles? Well, we recognize that the triangle 1 square root of 2 has angles pi over 4 inside. Let me mention at this point that unless specified otherwise, if you're asked to solve a trigonometric equation, then your answer should be given in radians. If the problem wants you to answer it using degrees, it will explicitly say so. Radians are the default when solving trigonometric equations. So we have that pi over 4 is the reference angle for both of these triangles, because that's the angle that sits inside a 1 square root of 2 triangle. And therefore, we can find two solutions. So, two solutions to the equation are pi over 4, so that's the first one, the one that sits in the first quadrant, and, well, we've got this other gamma here, and we see that the green reference angle pi over 4 goes from this left gamma down to the angle pi. So here gamma will equal pi minus pi over 4. So it'll be 3 pi over 4. So the two of the solutions to this equation are pi over 4 and 3 pi over 4. So now that we've got this, we can find all of the solutions to this equation. Now, the reason why there are more is because, of course, there are infinitely many angles that all have the same terminal side. And so any angle that has the same terminal side as either of the two angles that we've already written are going to have the same cosecant, and so they're also going to be solutions. So the fact that pi over 4 is a solution means that pi over 4 plus 2 pi n are solutions for integers n. So this means we're going to take pi over 4 and add or subtract 2 pi some number of times. We're either going to add 2 pi n times, or we're going to subtract 2 pi negative n times if n is itself negative. And similarly, 3 pi over 4 plus 2 pi n are solutions for integers n. And that's actually our solution to the problem. This is how we'll want to write down the solution here. The equation cosecant gamma equals square root of 2 has infinitely many solutions, but they all lie in one of these two families. They all look like pi over 4 plus 2 pi n for some n, or 3 pi over 4 plus 2 pi n for some n. So this is the general strategy that we use when we get down to an equation of the form trig function of an angle equals a number. Now there is one small difference that we get if we happen to be working with tangent or cotangent. Things work very slightly differently. So let's look at another example. Let's solve tangent of theta equals square root of 3 for theta. We're still going to do the same sort of thing that we did before. We want to find solutions to tangent of theta. However, this time notice that the period of tangent is pi. One of the things that means is that we really only need to look in two quadrants for solutions here. So we only need to look in two adjacent quadrants covering a total angle range of pi. In order to find the solutions that we can use to build our entire solution set. So, given that we only look in quadrants 1 and 4, we could also use quadrants 1 and 2, by the way. But given that we're looking at quadrants 1 and 4, we know that tangent is positive in quadrant 1. So, let me do that slightly shorter. So that means that we could be looking for a theta like this. Now we know that tangent is equal to opposite over adjacent, and therefore we can label this triangle with a square root of 3 over 1. This triangle will have a tangent value, or this angle, theta rather, will have a tangent value of square root of 3. The hypotenuse here is going to be 2, and again we recognize this triangle. This is a triangle with inside angle measures of pi over 6 and pi over 3. Because theta is opposite the square root of 3 side, it has the larger angle, because square root of 3 is greater than 1. Therefore, theta is going to be pi over 3. So, we get that pi over 3 is a solution, or we can be even more precise, it is the only solution in the interval from negative pi over 2 to pi over 2. That is an interval with a total length of the period of the function. So that means that if we take pi over 3 now and we add pi times n, these are all solutions. And the reason why we can add just pi here is because pi is the period of tangent, which means that if tangent of theta equals square root of 3, then tangent of theta plus pi will also have to be square root of 3, tangent of theta plus 6 pi will also have to be the square root of 3, and so forth and so on. If you add or subtract pi any number of times to theta, that doesn't change what tangent of theta is. So if pi over 3 is a solution, then pi over 3 plus pi n are also all solutions. And in fact, they are all of the solutions. So there's how we handle it. So the first method that we use, where we find all of our solutions and add 2 pi, that works for sine, cosine, secant, and cosecant. And this method, where we add pi, where we find all the solutions within an interval of length pi and then add pi, n, works for tangent and cotangent. It's all based on the period of the function. Now let's look at some more complicated problems where we need to use a little bit of algebra in order to solve it. So this next one, we're going to have to use algebra. We're also going to have to use we're also going to have more solutions than we got last time. So let's look at the following. Let's solve 4 sine squared x minus 3 equals 0 for x. We want to find all solutions to this equation. Well, as I mentioned at the beginning, our main strategy is going to be turning equations into ones that look like the equations that we were just dealing with. That is, some trig function equals some number, so that we can then go build our triangles, find our reference angles, and move from there. So let's do that here. So first, we're going to use algebra to isolate the sine squared term by itself. So we'll add 3 to both sides, get 4 sine squared x equals 3. Divide by 4, get sine squared x equals 3/4. And now here's where we remember that sine squared x is just another way of writing sine of x squared. So to get sine of x by itself, we're going to want to take the square root of both sides. But remember that when we introduce the square root, we have to include a plus or minus. So if sine squared is equal to 3/4, that means that sine has to be the square root of 3/4 or negative the square root of 3/4. Let's simplify this a little. So sine x is plus or minus the square root of 3 over the square root of 4, which is just 2. So at this point, we have 2 different solutions here, actually. We have sine x is equal to square root of 3 over 2, or sine x is equal to negative square root of 3 over 2. Now, we'll want to handle these 2 cases separately, although, of course, there's going to be some symmetry which we can take advantage of. All right, so let's start with the first one. If we've got sine x is equal to the square root of 3 over 2, then sine is positive, which means that we're looking at angles which sit in quadrants 1 and 2. And we can sketch these out. The opposite side of these angles are going to be square root of 3. The hypotenuse is going to be 2, which means that the 2 sides are going to be 1 for the triangle in the first quadrant and negative 1 for the triangle in the second quadrant. Now this is a 1, 2 square root of 3 triangle, which means that the reference angle inside these 2 angles is pi over 3 in both cases. Now x itself will be the angle that starts at the positive x-axis and rotates around to get to the red rays that we've sketched. So we have the solutions of pi over 3 and 5 pi over 3. These are the solutions within, 2 pi over 3. sorry, I had a typo there. So these are the solutions within the interval 0 to 2 pi for this first equation here. And the 2 pi over 3 here comes from the fact that this is pi minus pi over 3. Because that larger green angle on the graph is pi over 3 short of being a half circle. All right, now let's look at the other one. Let's look at sine x equals negative square root of 3 over 2. This is going to work very similarly. Let me use a slightly different color though, so as not to be confusing. So with negative square root of 3 over 2, we're going to do the same sort of thing where we're going to look at each of these triangles and make sure that the angle near the origin has a sine of negative square root of 3 over 2. Remember that the hypotenuse is always positive when we set up our triangles this way, and the opposite side, therefore, is going to be negative square root of 3 in each of these cases. But that makes sense because the vertical sides for each of these triangles are going down from the x-axis, therefore they should have a sign of negative. And so these two blue triangles are also 1, 2 square root of 3 triangles, and so the reference angles inside are again pi over 3. So let me use the yellow to indicate both of these angles. So we get this angle coming around like this. So that first angle will be pi plus pi over 3, which is 4 pi over 3. So that's because this is pi plus pi over 3. And the second one we can see is 5 pi over 3, and that's because it's 2 pi, the whole circle, minus pi over 3. So these are the solutions within the interval 0 to 2 pi. So that means that for our whole equation, we have now 4 solutions that appear within the interval from 0 to 2 pi. Now, some problems will actually just ask you for the solutions within a certain interval, such as 0 to 2 pi. If that's all the question's asking, then that's how we would end it. We would just give these solutions and move on. However, we have more to do than this, because the problem just asked us to solve the equation, which means we need to give all the solutions. So that means that our true solution is going to be pi over 3 plus 2 pi n, because 2 pi is the period of sine. Pi over 3 equals 2 pi n. 2 pi over 3, I'm sorry, not equals, but plus 2 pi n. 4 pi over 3 plus 2 pi n, and 5 pi over 3 plus 2 pi n. So this equation has 4 families of solutions for n and integer. This equation has 4 families of solutions that are each based on some solution to the equation that occurs within a single interval with length equal to the period of the original function, which is what we are working with. All right. Now, there are some simplifications that can be done. One thing that you might notice if you look at this type of problem in books is that these two solution families could be combined. We could describe this whole family of solutions as pi over 3 plus pi n for n an integer. And this doesn't mean that the original function has a period of pi or anything like that. It just means that these two families of solutions happen to match up in this way. Let's see how that works. If I start listing out the elements of each of these families, we get pi over 3, and then we add 2 pi, and which is 6 pi over 3, we get 7 pi over 3, and we add 2 pi, and we get 13 pi over 3, etc., etc. And then if we look at the family 4 pi over 3, and we add 2 pi, that will give us 10 pi over 3, and then we add 2 pi, which gives us 16 pi over 3. And of course, we also have the negatives as well. But what I want to notice is that if we compare the elements on the top row here with the elements on the bottom, I can get from the one on the top to the one on the bottom by adding pi. Pi over 3 plus pi is 4 pi over 3. Then I can get back up here by adding pi, and then get down by adding pi. And this pattern continues as we go on. So the point is, rather than listing these two sets of this set of solutions and two separate families, two separate strings like this, separated by 2 pi each, because these happen to line up exactly perfectly, pi apart from one another, we could have moved basically from here to here to here to here to here to here, and move on this way just by adding pi each time, and we'd get exactly the same solutions, just written with a single line, written as a single family rather than as two families originally. And we can do the same thing with the other two families in the original problem, actually. We could combine the second and fourth families to be 2 pi over 3 plus pi n. This is something that you will often see done, and if you spot this, if you spot that you can simplify your collections of families by combining two collections into a single one, by switching what you're adding at the end, then it does make things nicer, but be very, very careful when you do so that you aren't making any sort of mistakes and you are still listing all the same solutions that you were the first time. All right, let's see an example of what happens when the variable appears inside the trig function, but not by itself. Let's solve the equation 2 cosine 2 theta minus square root of 3 equals 0. So our first strategy is still the same. We're still trying to get the trig function by itself, but there's this 2 theta that's inside that's different than just the variable that we had before. So let's see how that works. As I said, we're going to start the same way. We're going to add square root of 3 to both sides, get 2 cosine 2 theta equals square root of 3, divide by 2, get cosine of 2 theta equals square root of 3 over 2. Now the best thing to do is actually introduce a new variable to stand for everything that's inside the cosine. Because we would know how to solve this equation if it were cosine x equals square root of 3 over 2. So let's just go ahead and do that, and then later on we'll come back and work out, well, okay, what do we actually do to handle the theta? So let's let x equal 2 theta. We just need to introduce some new variable that stands for everything inside the trig function so that we can solve for this new variable x and then go back to theta. So we get cosine of x equals square root of 3 over 2. We can solve this the same way that we have been. So square root of 3 over 2 is positive. Cosine is positive in quadrants 1 and quadrants 4. And if we graph this out, we'll want an adjacent side of square root of 3, an opposite side of 2, a hypotenuse of 2, which means we want an opposite side of 1 on the top triangle and negative 1 in the bottom triangle. So here are our two angles that give us a cosine of square root of 3 over 2. Now, we don't always have to use the interval from 0 to 2 pi to express our answers. In this case, it's a lot easier, actually, to use the angles pi over 6, pi over 6, and negative pi over 6. So our solutions here will be pi over 6 and negative pi over 6, and then we'll add 2 pi n to both sides. It's okay for us to include a positive and a negative. We just need to make sure that we include both solutions, or to be more precise, all solutions to this equation that occur within the whole, within a whole rotation of the circle around the origin. So we can use pi over 6 and negative pi over 6. Of course, we could have also used 11 pi over 6 as well instead of negative pi over 6, but that would give us the same family of solutions. Notice that if we look at negative pi over 6 plus 2 pi n and 11 pi over 6 plus 2 pi n, these are going to give us the same collections of numbers. We'll get a negative pi over 6, adding 2 pi gives us 11 pi over 6, adding 2 pi again gives us 23 pi over 6, subtracting 2 pi gives us negative 13 pi over 6, so forth and so on. If we look at 11 pi over 6 and add 2 pi a bunch, that'll give us 23 pi over 6, so forth and so on. Subtracting 2 pi will give us negative pi over 6. Subtracting 2 pi again gives us negative 13 pi over 6, so forth and so on. So notice that, in fact, these two expressions, when you let n be any integer, or all integers, gives us the same collection of solutions, and so we can use either one that we want. All right, so coming back after that aside, our solutions that we have are x equals pi over 6 plus 2 pi n, and x equals negative pi over 6 plus 2 pi n. But we're not done. The original problem asked us about thetas. We have solved for x's. Here's where we need to translate back. So if x equals pi over 6 plus 2 pi n, and x is equal to 2 theta, that means 2 theta equals pi over 6 plus 2 pi n. So now to solve for theta, what we'll do is we'll multiply both sides by 1/2. Multiply both sides by 1/2 because that will cancel out with the 2 that's being multiplied by theta. So 1/2 times 2 theta is just theta. And then if we multiply 1/2 on the other side here, we just treat n as its own variable. And we'll get pi over 12 plus pi n. And that's one of our families of solutions. And then similarly, if x is equal to negative pi over 6 plus 2 pi n, that means that 2 theta equals negative pi over 6 plus 2 pi n. We'll multiply by 1/2 on the left and on the right side of the equation and get theta equals negative pi over 12 plus pi n. So at the end of the day, our solution is that theta equals pi over 12 plus pi n, or theta equals negative pi over 12 plus pi n for n an integer. So this is the general strategy when the argument of your trigonometric function is not just a single variable, but some expression of variables, is just replace that whole expression with a single variable, solve the equation that you get out of that as normal, and then go and use the substitution that you did with the solutions that you found to solve for your original variable. So in this case, to solve for theta. All right, let's do one last example where we see how we need to use both a trigonometric identity and some algebra in order to solve our problem. Let's solve the equation cosine x plus 1 equals 2 sine squared x. Now, solving equations that involve more than one, or that involve two different trigonometric functions is hard. Generally, you want to try and find some way to manipulate your problem, algebraically manipulate it to reduce it to the case where you are just considering one trig function at once. Now, this is not always easy to do, and it can take some cleverness to make happen. One thing to keep in mind is that we always have a way of transforming a squared trig function into a squared into an expression involving a squared trig function, some other squared trig function, via the Pythagorean theorems. So the Pythagorean theorems, or the Pythagorean identities, I should say, the Pythagorean identities allow us to transform expressions involving sine squared into expressions involving cosine squared, and vice versa. Similarly for tangent squared and secant squared, and for cotangent squared and cosecant squared. So for instance, we have that sine squared x plus cosine squared x equals 1. But that means that sine squared x is equal to 1 minus cosine squared x. What this means is that whenever we see a sine squared x in our problem, we can replace it with a 1 minus cosine squared x. That's going to be helpful in this case because it will allow us to transform our equation to one that involves only cosines. So this will give us cosine x plus 1 is equal to 2 times 1 minus cosine squared x. So that means cosine x plus 1 is equal to 2 minus 2 cosine squared x. So now we've got our expression in terms of just cosines. However, we have both cosine to the first power and cosine to the second power, which means we need to treat this like a quadratic equation from algebra. It means that we're not going to be able to solve directly for cosine. We're not going to be able to get just cosine equals some number out of this. We're going to need to either use factoring or the quadratic formula to make this work. And when that's the case, remember from algebra that the first thing you want to do is to get 0 on one side of your equation. So let's go ahead and add 2 cosine squared theta to both sides and subtract 2 from both sides. So moving everything over to the left, we'll get 2 cosine squared x plus cosine x minus 1 equals 0. So we've managed to translate our original problem into this one, and so now we want to know how to solve this. Now, if you're getting confused at this stage in the process, one trick that you can use to make things simpler is to introduce a variable to stand just for cosine. That can turn the problem into one that looks familiar. So we can do something like this. Let's let a equal cosine x. Then our equation becomes, or we can express our equation as 2a squared plus a minus 1 equals 0. And now at this point, we need to solve for a. And then when we're done with that, we'll come back and talk about the cosine. Now, in this case, this equation factors. And if you factor it, then you'll get what you need. So let's factor. I should point out that you can also use the quadratic formula here, but I do want to look at how the factoring works. So 2a and a, and then we'll get negative 1 and plus 1. Oh, whoops, sorry, I got that backwards. Negative 1 plus 1, which is how this quadratic expression on the left factors. Now we have a product of 2 expressions equals 0. The zero factor theorem tells us that that means that either the first factor equals 0 or the second factor equals 0. So solving for a in each of these cases, we get that a is equal to 1/2 or a is equal to negative 1. All right, this is all great, but now we need to come back to working with x because that's the variable that we're trying to solve for. So now we've got 2 possibilities, either cosine x equals 1/2 or cosine x equals negative 1. Let's handle each one of these separately. So for cosine x equals 1/2, we'll do this the same way that we did before. We will sketch out a couple of triangles in quadrant 1 and quadrant 4 because we're looking for a positive cosine, and cosine is positive in those quadrants. Cosine is adjacent over hypotenuse. And so we get these triangle ratios here, which tells us that this angle is pi over 3. This angle is negative pi over 3. So our solutions to this first part are x equals pi over 3 plus 2 pi n, or x equals negative pi over 3 plus 2 pi n. And now for the other possibility, for cosine x equals negative 1, For values of the trig functions that are 0, 1, or -1, we don't typically draw a triangle. We think of things in terms of the unit circle. And so if I sketch a unit circle here, I know that cosine, a cosine value of -1 occurs over here on the negative x-axis, because that's where the x value of the point on the circle is -1, and that has an angle of pi. Now, in this case, cosine x equals -1 has only one solution within the interval 0 to 2 pi, as opposed to the two solutions we normally expect. So we get that cosine x equals -1, which means that x is equal to pi, but of course pi is just what we get within the first revolution of the circle. We still have to add 2 pi n. So that means that our solution to this equation involves 3 families of solutions: pi over 3 plus 2 pi n, negative pi over 3 plus 2 pi n, and pi plus 2 pi n. This is another one that could be simplified down quite a lot. In fact, if we combine all these things together, we see that we could write all of it as x equals pi over 3 plus 2 pi over 3n, but that's not really that's not real easy to see. So we definitely don't need to write it down that way, but if you're interested, take a look and see if you can understand and see why it's the case that we can actually write down all 3 of these families of solutions using just a single expression here.